Hello everyone, welcome to what will be pre-lecture number 32. We're going to talk a little bit more about solubility that we didn't quite get to last class, and then introduce colligative properties. So before we get into that, just want to plug again, I'll do this in class as well, but want to make sure you're aware, make sure you're going to the research week activities that are all this week. And also, if you have an interest in engineering, make sure you are heading to that meeting tomorrow, Thursday, November 10th. And if you have any questions, feel free to email me or Professor Bentley about engineering. Okay? All right, getting into the chemistry, we left off last class talking about solubility, differentiating between compounds that are either totally soluble, that have a maximum concentration above 0.1 molar, slightly soluble things that have a maximum concentration between 0.001 molar and 0.1 molar, and then insoluble things that have a solubility below that level. And sorry, when I say solubility there, I should mean maximum solubility or maximum concentration that can be dissolved. Okay? Along with that, I also want to talk about when things are saturated or unsaturated. So when a solvent is capable of dissolving more solute, it is unsaturated. But once everything has possibly dissolved in a solvent, as is possible, and say if we were dissolving salt, say there's some salt left at the bottom of our glass that is just no longer dissolving, we would call that saturated. Okay? There is one other situation that is actually supersaturation. And so this is when a solvent actually dissolves more solute than it would normally be able to, but this happens at a higher temperature or pressure than it is currently at. And so kind of a classic example of this is carbonated beverages that are a supersaturated solution of carbon dioxide in water. And then when we pop a can or turn the lid on a bottle, a lot of that carbon dioxide is released. That's why you get bubbles when you open things, because we have lowered the pressure, and so our supersaturation ceases as carbon dioxide comes out of solution. Okay? All right. Another thing I want to talk about are solubility rules, and so I could read this off to you, but I will allow you to read it on your own time. This is going to be important to know going forward for not just general chemistry, but really all things chemistry, basically what sort of things are soluble or insoluble as far as ionic compounds go. And so we have soluble things, kind of the pattern I will point out are things like sodium and potassium that have a +1 charge in our first column of the periodic table, as well as ammonium, this NH4. Pretty much always make soluble compounds. Same thing with nitrate, NO3-, chloride, bromide, and iodine are almost always soluble. With the halides, the chloride, bromide, and iodide, only exceptions to those are lead, mercury, silver, and then copper 1+. Okay. Finally, sulfate, usually also soluble, but we have basically some of those same exceptions there. Okay. As far as insoluble things go, most things that are insoluble are sulfides, oxides, or hydroxides. The exceptions to that tend to be what we listed up here for things that are normally soluble, right? Our sodiums, our potassiums, our ammoniums, and we have a couple of other exceptions there, okay? One that you do not need to know is chromate. I'm giving you that one as a freebie. I won't ask you about it, but things like phosphates and carbonates, you should know those are not typically soluble, okay? Except with our, of course, exceptions, okay? We'll talk a little bit more in class and do some practice with that as well, but this is something that you'll probably just need to memorize, okay? All right, another thing I want to talk about in this pre-lecture video are a few different ways we can measure quantities. And so wanted to start by talking about mole fraction. And so it's a pretty simple concept. As the name would imply, we are in units of moles, and we are determining a fraction, which is always a part of the whole. So anytime we determine the mole fraction of something, We take the moles of whatever that compound is. In this case, I'm just saying A, so A can be any molecule or element, any compound. And we take that number and divide it by the total number of moles for all of our components. Okay? And things like mole fraction become important when we start to think about partial things. So partial pressure is something that we could have talked about with regards to gases, but I figured it would actually fit in better here. And partial pressure is essentially the same exact thing as pressure, but we are looking again at one specific type of moles. And so all of the moles and their partial pressures together add up to our total amount of pressure. But to calculate the partial pressure, we just take or this is our partial pressure then, this P sub A, and that is equal to the number of moles of that specific molecule, whatever it is we're looking at, with regards to the total of the whole, and then times our other constants, or not necessarily constants, but parts of our PV equals nRT equation. Okay. Finally, last new quantity I want to talk about today is molality. So similar to molarity, but instead of an uppercase m, we use a lowercase m. And it is defined as the ratio of the number of moles of something we have, but instead of being per liters of our solution, molality is the moles of solute per kilograms of solvent. Okay, so that's a little bit of a different unit. We have mass as our bottom, and it is kilograms of solvent. Okay, and that will come in handy here in just a moment. All right. Why do we care about all these things? These new properties, they lead us to a discussion of colligative properties. And so colligative, kind of a weird word, you've probably not heard of it before, but what it means is these are properties that are related to the total solute particles dissolved in solution. And something that is important to note is that it does not depend on the identity of those solute molecules, just the total number. Okay? So the ones we're going to talk about in Gen Chem here are vapor pressure depression. So we talked about vapor pressure last week as basically the pressure of gas above a liquid that is in equilibrium. And as our solute dissolves, our solution's vapor pressure is going to be lowered or depressed relative to that of the pure liquid. Okay? The reason this is because we have less liquid molecules that are able to escape the surface of our liquid and become gases, and so that is what vapor depression is. We'll talk a little bit more about that in this video. We also have boiling point elevation. This is basically the flip side of vapor pressure depression. If we have less liquid molecules that are able to turn into gases, that is also going to raise the temperature at which our substance, or our solution, I should say, boils. That is, again, because we are less able to have our liquid molecules turn into gaseous molecules. So our boiling point is raised relative to the pure solvent. We also have a change in our freezing point. So that is a depression, meaning it is lowered. And that is because our solute molecules will interfere with the intermolecular forces between our solvent molecules during our freezing phase transition. And then our final one is osmotic pressure. And so this is a pressure measured across a semi-permeable membrane between different solutions with different concentrations of solute particles. And so we'll dig a little bit more into all of these, starting with vapor pressure. Small meme for you. But again, it is something, if we think about this visually, if we have a pure solvent, we have an equilibrium that creates a certain pressure in our gas molecules. We call that the vapor pressure. And there's an equilibrium between liquid and gas. But when we have a solute in our solution, some of the spots where that liquid could turn into a gas are going to be occupied, and that is actually going to lower our vapor pressure. Okay? And like many things in Gen Chem, we want to be able to describe this mathematically. We do that with something called Raoult's law. That's here, where our PA is our partial pressure of whatever our gas is. We multiply that by the mole fraction, and then PA star is just the vapor pressure, or the partial pressure of the pure solvent. Okay, so pretty simple relationship there, but that is how we adjust for partial pressure when we have a solution. Okay. Next up, boiling point and freezing point changes. And so we talked about these conceptually. If we talk about boiling point, our changes in boiling point temperature can be measured by multiplying some constant. This is the boiling point elevation constant. I would, of course, give that to you by I, which is the total number of particles in our solution, and then the molality. And so we'll, again, practice this in class, but I becomes important when we have ionic compounds that dissociate to form multiple particles in water compared to covalent compounds that just simply dissolve without dissociation, right? And we have a corollary there. You'll notice this equation looks very similar for freezing point, where we have a change in our freezing point temperature, a depression, where we take a different constant, so this is a constant related to the freezing point, and then multiply it by the number of particles in solution and the molality of that solution. Okay? Take-home point here is that with these colligative properties, all of our solutions will remain in the liquid phase longer when they have solutes dissolved in them. And if we were to represent that with something else from last week, we can look at a phase diagram, right? And so the solid lines here, this solid blue line, represents basically if we had the pure solvent, and then as we dissolve solutes in that solid, you can see that as we go between a liquid and a solid, our freezing point is depressed, meaning it's lowered, so we're a liquid longer, and our boiling point is raised, meaning that we lower our barrier here, and so our take-home point, again, we're in the liquid phase for a longer time, no matter which way we're going. Okay? All right, so one last thing for our pre-lecture video is osmotic pressure. We represent this with the variable uppercase pi, so that's actually the uppercase of the Greek letter pi. And it's a difference in hydrostatic pressure across a semi-permeable membrane caused by differences in solute concentration. With osmotic pressure, we calculate it with this equation here, where that osmotic pressure is equal to the concentration and molarity times the ideal gas constant, R. So it is a gas constant, but it can also be used actually for osmotic pressure, and then temperature as well. And of course, our temperature has to be in Kelvin anytime we use our ideal gas constant. If we think about this pictorially, say we have a pure solvent on one side, a semi-permeable membrane, and we have a solution on the other, what's going to happen is our pure solvent is able to cross that membrane, but our solute molecules are not going to be able to do that. And so through diffusion, we're going to end up diffusing more of our solvent molecules over across our semi-permeable membrane, and we're going to get a difference in osmotic pressure there. Okay. Some people asked about this sort of idea last class as it relates to biology, so we'll discuss this more in class itself. But this is essentially what happens if you're dehydrated or overhydrated. You can get swelling or compression of your red blood cells based on if you don't have a balanced amount of solute particles dissolved in your blood. And so that can affect the size of your red blood cells, which can, if they're overswelled, lead them to burst, and otherwise lead them to compress and not be as effective at carrying oxygen. Okay, so a little biological application there for you. Anyhow, that is it for our pre-lecture. I hope that was useful. If you do have any questions, please let me know. Otherwise, I will see you in class.